That's our topic today. And we start with objectives of the topic. We'll define radioactivity, decay, and half-life. Describe the 3 types of radiations emitted, how they are detected, so explain the detection. What you're supposed to do is define also nuclear fusion and fusion, right balanced nuclear equations, explain the dangers of radioactive emission, state applications, and then solve a few numerical problems. That is our content. So I will move on to that. What is radioactivity? So radioactivity is the disintegration of unstable nucleus with the emission of radiation in order to attain stability. Now we all know, if I relate with your chemistry part a bit, we normally say when an atom is unstable, it will either lose electrons or gain electrons. But for radioactivity, we are looking at the nucleus of that atom, of the nucleide. Now, if the nucleus of that atom is unstable in terms of the number of neutrons and protons not being at a ratio of 1:1, then that is the time we say that that nucleide is unstable. Now, let's just, before even go into that, let's look at the structure of an atom. I want to believe you have done that in your chemistry, and I know in chemistry it is done very well. So we have there, the nucleus is very small. The number of electrons in the shells is equal to the number of protons in the nucleus, and making that atom to be referred to as electrically neutral. When you talk about an atom being electrically neutral, it simply means the number of electrons is equal to the number of protons. That is from your chemistry. We go to definition of a few terms. I want to believe in your chemistry you have defined the atomic number as the number of protons in the nucleus of an atom. We have mass number there, which is not bold. The mass of protons and neutrons in the nucleus of an atom. Isotopes, it is there. Those are terms you have already encountered in your chemistry. The definition is still the same. And then nuclear maybe is what you have not, a group of atoms that have the same atomic number and the same mass number. So now let's look at the real thing here. Nuclear stability. Now, when we say a nuclide is stable, it simply means or indicates that the proton-neutron ratio is 1:1. That nuclide is said to be stable. Now, if the ratio is not 1:1, then we are going to say that that nuclide now at that point is unstable. And what it will do, it will decay by releasing the radiations we're going to look at for it to gain the stability. If you look at the graph there, the graph that you've been given at that point, oh, sorry, let me go back. If you look at that graph, there's that bold line. There's a line, indicated line of stable nucleus. nuclides, and then there's regions occupied by unstable nuclides. So there are any nuclide below or above that bold red line is unstable. That is, the ratio of the neutron, proton-neutron is not 1:1, and therefore it is on the other side. Either if it's on the upper side, the number of neutrons is more than the number of protons. If it's on the lower side, the number of protons is greater than the number of neutrons. And therefore, during its decay, or during when it disintegrates in an attempt to achieve stability. We move on to radioactive decay. So this is a process by which a radioactive nuclide undergoes disintegration to emit a radiation. Now, the radiation which is emitted can be an alpha particle, a beta particle, and then accompanied by gamma radiations. Gamma radiations are energy. Who is that now? So, emission of alpha, beta, and gamma radiations. Now, types of radioactive decay which you have done. So, alpha decay is represented by helium, or denoted by alpha. There's alpha there. There's a symbol there. That symbol is alpha. Helium 42He. So anytime you're writing an equation and you're being told that it was an alpha particle which was released, you represent the alpha particle. You can represent the alpha particle using the helium 24 or the symbol of alpha. But the best is because you're going to write an equation, you use the helium. Now, on that equation represented there, we have the parent nuclide, we have the daughter nuclide, and the particle which has been released. If you look at the bottom there, there's an equation of uranium. We have uranium there. Yes, we have uranium, which has decayed. Uranium, for example, decays by emitting an alpha to become thorium. Now, if you add, go to the, is it your left-hand side, where the side of thorium and helium, if you add 234 plus 4, it will give you 238. If you add 90 plus 2, it will give you 92. In other words, they should balance on both sides. So that is the equation. Griffins Mugambi, yes. I can see you've raised your hand. Yes, Griffins. Griffins Mugambi.
A second, Madam Oeri. There is a student here. We don't have a name. It doesn't need to be a name of the student in school. If he's listening, kindly use your proper names to participate in class. Use your proper names. And if you don't, then you're going to be out of class anytime. Thank you, Madam. Proceed.
Okay. So we have that equation there where an alpha particle has been emitted, and that's how we write the equation. We move on. The next part, we have another equation where we're having polonium undergoing an alpha decay. It gives you lead 206, and an helium particle is definitely emitted. Now, when you go to beta decay, beta is assumed to be negatively charged. So it is represented using an electron and denoted by that symbol, which is the beta symbol. We have the equation there of how you could write an equation of a decay where a process where beta is being emitted. We have the parent, daughter, and the beta particle. Let's go and use the real equation. We have sodium there. Sodium, it decays by releasing a beta particle, which is represented by 0, -1. And then we form magnesium 2412. If you add your left hand side should be equal to the number on the right hand side. I am moving on. Before I move on, for gamma, I'm seeing Griffin Mugambi. Yes, Griffin Mugambi.
So in the in the previous slide, in the example that you're showing X, and then the way it decomposes, it had shown.
Which one? Not decomposes.
In the example for the parent nuclide, I can see the alpha, the mass number is 2 and the N is 4. Is it correct or there's a mistake?
That is a mistake. It's supposed to be 4. You can see down here I have 4 too.
Okay, thank you.
When I wrote up there, it is 4 2. This is just a typing error. Just a moment. Let me see if I can. I cannot do it now, but it's supposed to be 4 2. Okay?
Okay.
Yes, just the way it is written up there. So I was saying for gamma radiations, when gamma radiations are emitted, because they only release energy, there will be no change in the mass in A or Z of the parent nuclide. It remains the same. That is the atomic number, and the mass number remains the same for gamma radiation. Now we have that example there. Let's look at that example. Thorium-230 undergoes decay to become random. Find the number of alpha particles emitted. It has been worked there. I don't know. Maybe you looking at it. I hope you can be able to understand. The equation is there. You are to write an equation because you are looking for the number of alpha particles. Remember, alpha is represented by helium. Again, your textbook has got quite a number of examples. You could also use that. After we are through with the lesson, you could also try and use it so that you see whether you to try and understand better other than what I'm doing, because I cannot be able to see what practically you are doing. I move on to the next. That's another example of lead-214, which decays to polonium-214 by emitting an alpha particle. So here we are emitting alpha particles. So you're determining the number of beta particles that have been emitted. Calculate the number of beta particles emitted. It is also worked. So that's another example. And as I've said, with the examples, please compare with the ones in your textbook. There are good examples there. Now I'm going to the properties of emitted radiations. Properties of the emitted radiations. We start with alpha particles. We assume they are positively charged, hence deflected by electric and magnetic field. They have low penetrating power, but high ionizing effect because they are heavy and move slowly. So since they are heavy and they move slowly, they will cause a lot of ionization on their way. When you're talking about ionizing effects, you're looking at the air particles, knocking off of electrons from air molecules. When you do that, then you cause there's an ionizing effect which is caused. Loss of energy, they lose energy rapidly. So they move, they cover, or the distance they cover is very short. They can be stopped by a thin sheet of paper. They affect photographic plates. Beta particles, they have no mass, negatively charged. We normally assume they are negatively charged, so they are deflected by both electric and magnetic fields. They have more penetrating power when you compare them to alpha particles, but low ionizing effect. Gamma rays, radiations, high energy, have no mass, no charge, so they are not affected by electric and magnetic field. High penetrating power, low ionizing power, can penetrate through a sheet of paper and aluminum sheets. Now I want you to look at the diagram below because I'm giving about, so that is our diagram in terms of deflection. When we are talking about alpha, beta being positively charged, then you're looking at gamma not having any charge. You can see they move through. Gamma travels, does not get affected by the electric or magnetic field, but the beta is deflected to the positive because it is negatively charged, while alpha is deflected to the negative side because it is positively charged. And the penetration, the diagram ahead there is for penetration. You can see alpha is stopped by a paper, beta penetrates paper and it is stopped by aluminum sheet, while gamma penetrates all the way to the lead. Now there's another diagram there. This one, the dots are representing the magnetic field. That's the magnetic. So these particles are moving through magnetic field, the field. The other one, let me take you back. This field here, the positive and negative is representing electric field. So the particles in the electric field. Now this one here is representing the particles moving through a magnetic field. So you can see beta is highly deflected. So the difference between X-rays and gamma rays is that the gamma rays originate from energy changes in the nucleus of an atom, while X-rays originate from energy changes associated with the electron structure of an atom. Remember when you're looking at X-rays, we said, how do you get to have production of X-rays? When you suddenly stop electrons which are in motion. But for gamma rays, as we are seeing, they originate from the center of the nucleus of the atom. That is what is there. Now I will not look at, let me jump the detectors first. We'll come back to it. Let me look at the tracks. That is, the track simply means how the beta, alpha, and the gamma radiations traveling through, for example, air. What are the tracks that they leave behind? What is it formed? So we start with the alpha particles. That diagram there are tracks which have been left behind by an alpha particle which was moving through air. So the tracks due to alpha particles are short, straight, and thick. Now, why are the tracks short, straight, and thick? Now, remember we said alpha particles is an helium particle which is heavier. So since it is heavy, it causes, because of its size, the ionization effect will be high. That is why it is thick. The tracks are thick. That is why the tracks are thick, because of heavy ionization along the path that it is moving. Now, why are the paths straight? Remember, they are also heavy. That means nothing can change their path. They are heavy, they cannot easily be deflected. And also, why are they short? Why are the tracks short? They are short because, remember, we said they are heavy and therefore they lose energy easily, and therefore they cannot cover a longer distance. That is why the tracks are short, straight, and thick. They are massive and their path cannot therefore be changed by the air molecules. Alpha particles cause more ions on their path as they knock off more electrons. So ensure that you can be able to explain that statement there, that tracks due to alpha particles are short. Why are they short? They are straight. Why are they straight? And then they are thick. Why are they also thick? The three give the reasons why they are thick. The next tracks are for beta. You can see the tracks of beta. They are not straight, they are not thick. The tracks formed by beta particles are generally thin and irregular. That is the main important thing there. Thin and irregular. Why are they thin and irregular? This is because beta particles, they are lighter and move faster. So they cause less ionization. That is why the tracks are thin. They cause less ionization. And irregular means they can easily be deviated by others. So in addition, the particles are repelled by electrons of atoms within their path. That is why they are not straight but irregular, because of that repulsion caused by electrons from other atoms along their path. For example, the air molecules, the electrons there can cause that. And lastly, the other type of track is that one, the gamma rays. They produce scanty, disjointed tracks. Remember, with the gamma rays, we said they are not particles, and all they produce is just energy. So their particles are, their tracks, not particles, their tracks are scanty and disjointed as shown on that particular diagram. Any question after there? Okay, if there's no question, we move on. I said with that will be covered later. Detectors. I want to move on to background radiation. Now, I know we have not jumped the detectors part, but a detector is a machine which can be used to detect that there is radiations in these, wherever you are. Now, for background radiations here, we are looking at, you are in a room and you are sure there are no any radioactive material there. But if, for example, you place the GM tube there, it will still click. Now, why does it click? It indicates that there is presence of radioactive. There are radiations there. Now, these radiations, which are there, so radiations are registered or observed in absence of radioactive source. There's no radioactive source within any close range, but then the GM tube still gives you registers counts. Now, where do these the clicks or the radiations, the background radiation come from? The source of background radiation, cosmic rays from outer space, radiations from the sun, rocks. We all know we are surrounded by rocks or other materials. They'll produce that. Then we have natural and artificial radioisotopes. So radiations are registered or observed in the absence of a radioactive source. The count register in the absence of radioactive source is what we referred to as background count. Sources of these background radiations are listed as I've given. And also in your textbook, I think they are quite they are there. I think they're also listed in your KLB. I move on now, and still under background radiations. No, that is still the same thing. We move on to artificial radioactivity. That is after background radiation, we move on to artificial radioactivity. Now, what is artificial? There is that natural radioactivity where a nuclide which is unstable will just decay on its own to try to gain its stability by balancing the ratio of the protons to the neutrons. Now, for artificial radioactivity is where you force a nuclide which is believed to be stable to become unstable. You bombard a stable nuclide with either neutrons, protons, or alpha particles and make it to be unstable. That is what we refer to as artificial radioactivity. So some naturally occurring nucleates can be made artificial radioactive by bombarding them with neutrons, protons, or alpha particles. For example, we have nitrogen-14 there, which we know is unstable. Then we bombard it with the helium or an alpha particle. We end up with unstable oxygen-17 and a nitrogen there. So other artificial radioactive nuclides can be silicon, sulfur, fluorine. Now, what we are saying in this case there, as long as you have an unstable nuclide, if you bombard it with any of those neutrons, protons, or alpha particles, it definitely become unstable by giving rise to unstable nuclide. Now, the decay law, what does it state?
Okay, let's do a quick roll call. Look at your screen. Confirm roll call. Quick. We are at 84%. I want us to do 30 boys to go. 25 more kids. No. We still have about 25 boys or not? Okay, 93. So we still have about 15, 14 now who have not submitted the roll call. 14 boys have not. And I think I'll just end there. Madam, you can proceed. Thank you.
So we were looking at the decay law. What does it state? Rate of disintegration at a given time is directly proportional to the number of nucleides present at that time. The rate of disintegration at a given time is directly proportional to the number of nucleides present at that time. Now, there's that equation here. Let me just highlight the equation. This is the equation representing, this one here is the equation representing what we have, the decay law we have stated there, where N is the number of nucleides present at a given time. Now, someone may ask, why do we have the negative sign there before N? The negative sign shows that the number N decreases as time increases. Time is increasing, but the number of nucleides is decreasing, hence the negative sign. Now, the first part, this one here, is the one which is talking about the rate of disintegration is directly proportional to the number of nucleides present. That is the rate, and then this is the number of nucleides. Definitely the N is the number of nucleides. Then we have, when we introduce an equal sign to that equation, we end up with that, the equation, the equal sign, where now K, where not K, but the inverted word, lambda, there represents, is a constant, a decay constant. And I need you to note that this is referred to as the activity of the sample. So if you come across it, it simply means that is what the rate of the activity of that particular sample that you have. Just a moment as I erase what I've done. So that's the decay law. You're going to okay. Now the next part, half-life. Now, what is half-life? Half-life is the time taken for half the number of nucleides initially present in a radioactive sample to decay. Time taken for half the number of nucleides present to decay. For example, if you have 10, half of 10 is 5. The time it takes for the decay to take to the number to reduce to 5, that's what we are referring to as half-life. The time it will take 5 nucleides to decay to half, which is 2.5, that time is what we are referring to as a half-life. So half-life of a radioactive cell can be determined using, we have that is this equation. But before I look at the equation, the one I normally for using, which is easier than that one, although Just a moment. Let me again use this. If you have the number of nucleides you have at a time is maybe 10. Half of 10 will be 5. Then half of 5 will be what? 2.5. Half of 2.5 is what? Hey.
1.25.
Yeah? What?
1.25.
So at this point here, that is a half-life T1. At this point here, this is our T2. And then at this point here, is our T3. So T1, T2, T3 are half-lives. Half-life simply means the time it takes to decay to a half that. And the number of nucleus might not be the same, but the time it will take that particular number of nuclei to decay to a half is what we are referring to as half-life. You could use this to solve a question, or use the equation given here. That will still work. Where n is the number of original count, in our case will be 10, not 10, the one remaining. N naught is the one which is 10, half. Capital T is the total time of decay. Small t represents half-life. So n let me change something here. This should be n naught. And this should just be n. So when you're using that equation, you ensure that you must represent all what has been represented in the equation. But I always insist, the easiest way is this way. This will never go wrong. Maybe I will try and see if we can get a question and do together. I move on. Now, what if you were to plot a graph of number of radiations or nuclei against time? You should end up with a curve looking like that. How do you determine the half-life? It is, again, you can see it is n, the original number, half of n, a quarter of n, and 8. All these are half-life. So if you are told to get the half-life of that, of maybe if our n was 10, half of 10 here should be 5. At this point here is the other way. Just a moment again. I'm saying this. In what we have been working, this can be 10, half of 10. This is now 5. Half of 5, this is 2.5. And half of 2.5 is 1.5. So again, at the same time, you could look at half-life in terms of in fractions. If we have a whole number, and the whole number I'm talking about here is 1. If the nuclide is a 1, half of 1 is what? Is a half. Half of a half is what?
40.
Half of a quarter?
An 8.
Half of an 8?
16.
16.
And you continue like that. All the in between, all these are half-life, this is another half-life, like that. So if maybe you're being told how many half-lives we need for it to decay to a 1/6, then you count this 1, 2, 3, 4. 4 half-lives for it to have to decay to a 6, 1/16. Again, you must understand there's another way somebody would ask that question. Either the remaining fraction or the fraction which has decayed. So you need to be able to understand what at that point, what is required by the examiner, and is it the fraction part, main part remaining, or what has decayed? I'll talk about the graph, how you determine half-life of your graph. You divide the number of nucleides present initially, and then you, yes. So I'll take you back. I want us to do to try a question on half-life. I want us to try a question on half-life. So I hope you have your, give me a moment. Trying to get your question. I want us to try half-life. Now, kindly write this question down. Then you do it. Then we try to. Are we ready to write? Given that 5 grams of cobalt 60, given 5 grams of cobalt 60 is kept in a laboratory and its half-life is 5 years. Given 5 grams of cobalt 60 is kept in a laboratory and it has a half-life of 5 years. Calculate its mass after 15 years. Calculate its mass after 15 years. I hope everybody has gotten that.
Yes.
Yes, write the answer. I can see answers. They are correct. That's correct. $7.5, no. How can it be 7.5? No, 7.5, no. Please go back and do it again. Yes, the rest, yes, I can see. 1.25, no. 1.25, no. 0.125, no. Remember, there are 3 half-lives. 15 is 3 half-lives. So it must decay 3 times. So the answer is 0.256 grams. That is what will remain. Next question. I hope people are trying. Randon has a half-life of 4 days. Randon has a half-life of 4 days. A sample of Randon has a mass of 40 grams. What mass of the sample will have decayed after 16 days? I repeat, Randon has a half-life 4 days. A sample of Randon has a mass of 40 grams. What mass of the sample will have decayed after 16 days? What mass of sample will have decayed after 16 days? Yeah, the answers I'm seeing are correct. So far, 35 no, 2.5 no, 2.5 no, 2.5 no. You have been asked what will have decayed, not what is remaining. Still more. We are so many. We are 211. More answers. Zero 0.75 no, 17.5 no. $27.5 no. $18.75 no. So the answer is 37.5. That is what is. Now, a next question. Next question. A sample of a radioactive substance has a mass of 2 grams and a half-life of 7 days. A sample of a radioactive substance has a mass of 2 grams and a half-life of 7 days. The question, what fraction of the original sample would be decayed after 21 days? What fraction of the original sample would have decayed after 21 days? A quarter, no. 1.5, no. Please kindly listen. What fraction of the original sample will have decayed? Not is remaining, will have decayed. 1/8, no. 1/3, no. 3/4, no. 1 3/4, no. Three over four, no. Three and 1/3, 0 3, no. 1/4, no. One and 3/4, no. Three-quarters, no. Eleven over four, no. I'm waiting for more answers. Waiting for more answers. Now, for that one, the answer is 7/8. That is the fraction which will have decayed, not the fraction remaining. Which will have decayed is 7/8. Remaining is 1/8. Please try to understand the language of the question. So I don't know, anybody, I don't know whether people are having problems in calculating that. Can you hear me now?
Yes.
Yeah.
Is there anything shared on your screen?
No.
No.
You can see now?
Yes.
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 Okay.
Yeah.
So sorry for that. They look at the detectors, okay? And I was listing them. No, it seems the next one is the cloud chamber. There's expansion cloud chamber and there's diffusion chamber. And then we move on, we have the GM tube, that is, we have the GM tube, the Ginger Miller tube, and then we have we have the gold leaf electroscope. So we are going to look at these detectors one by one. Maybe we might not be able to finish them. If we don't finish, that means you'll finish in class. So I was starting on the first, like when you go for X-ray, you're required to present an X-ray plate. That is the material they use. So all the three radiations affect the photo. To workers who handle radioactive material, that's why they're able to detect the amount of radiation they have been either in a shot. So if they're exposed to too much, they're able to detect that there's too much, or the amount photographic film. If during the time it had been worn, the worker should be taken. That is the photographic emulsion, one of the detectors which can be used. The three affect. Now, the next one is the cloud chamber. But before that, let's look at what is a cloud chamber. When air is cooled until the vapor, without condensation occurring. Under these conditions, the vapor is said to be supersaturated. This can only occur the first type, expansion cloud chamber. That is a diagram of the expansion. Or pushed in so that there is going to be a producing whatever radiation, whether alpha, beta, or the gamma. Now, when the radioactive element emits the radiation, there inside, if the piston is moved down suddenly, the word there is suddenly, occur. When this happens, the ions formed, remember ions are formed due to the saturated alcohol or water vapor condenses, forming the tracks. You will be able to see the track. So you will be able to see the tracks. So from the tracks, you'll be able to identify which.
Teacher, you are breaking. I cannot hear you clearly.
Yes, just a moment. Let me check my network. Okay, I've changed. Now I'm saying, remember, the radioactive source releases either the alpha or the beta particles or the gamma rays. As the particles travel through that chamber, their inside is ionized. They knock off air electrons from the air particles. So the air gets ionized. So When now you suddenly pull, we are talking about when the piston is moved down suddenly, there in the chamber will expand and cooling will occur. The cooling will take place on the ionized air particles. They act as the nuclei on which the saturated alcohol, we have their alcohol, or the vapor there can either be for alcohol or for water. And tracks are formed. The outline of the tracks are formed. So you can be able to identify, is it an alpha particle? Is it a beta particle? Or a gamma particle being formed? Is that okay? You'll go through in your notes also. The next one is the diffusion cloud chamber. That one there, the diagram is there. This is very important. By the way, you need to have those diagrams and ensure that you can be able to name each part. Now for this one, you should be able to name the black velvet, the sponge, the radioactive source, perspex lead. Now the functions of those components. We have dry ice. We have dry ice. What is the function of the dry ice? Cools the blackened surface, making the air at the lower surface of the chamber to cool. I can see on the diagram, these small like particles here, that is the dry ice. Kindly, it is not labeled. But you could also refer to your textbook. The same diagram is in your textbook. Now, what is the function of the sponge? It ensures that the dry ice is in contact with the blackened surface. The wages definitely to balance. The chamber light source illuminates the tracks, making them clearly visible. And then the blackened surface provides better visibility of the tracks formed. Now, how it operates, how the diffusion cloud chamber works. So we are told there that the alcohol from the filterings, please note the filtering. Where are the filtering? Yes, the filtering soaked in alcohol. So the alcohol from the filtering evaporizes and diffuses towards the black surface. The radioactive substance emits the radiation which ionizes the air. Ionization is a key important part here because it is at the ions which have been formed due to ionization of air that condensation will take place, and you'll be able to see what the tracks that you're supposed to be observing. The vaporized alcohol condenses on the ions, forming tracks. The tracks are well defined if an electrical field is created by frequently rubbing the perspex lead. The perspex lead is there. If you look at that, is the perspex lead. So what you do, you rub it. You know very well from your electrostatics one, if you rub that perspex lead, it becomes charged. So it will bring about the electric field. Electric is created by frequently rubbing the perspex lead of the chamber with a piece of cloth. The track obtained in the chamber, you can be able now to identify, is it an alpha, is it a beta, or a gamma? Now, why is alcohol preferred? It is highly volatile and hence easily evaporates. That is why we use alcohol in this case. Any question up to there? So we have done 2 detectors. photographic, and the cloud chamber. Under the cloud chamber, there are two: expansion cloud chamber and the diffusion cloud chamber. The remaining is the GM tube, which you will do. I think from there you will do it in class. I will want to beg and stop there. The GM tube you do in class, but that is how the GM tube looks like. And the gold leaf, we're doing that in class. Any question after there? Because I want to stop the lesson at this point.
Thank you so much, madam. We appreciate your time and sharing a lot of important things. Boys, have you learned something?
Yes. Yes, we've learned something.
We have. Very good.
Yeah.
So you can go ahead, have a rest afternoon, and remember we're meeting tomorrow morning. If possible, arrive early. I'm noticing majority of you are coming late. Actually, 30 minutes into the lesson. You want to get better, be on time, and then leave on time. Salimia wazazi.
Thank you, sir. Thank you, Mwalimu.